October 1943. A P-47 Thunderbolt pilot at 28,000 feet over Germany begins to feel euphoric, almost drunk. His vision narrows. His reactions slow. He doesn't realize he's dying. Hypoxia, oxygen starvation, is killing him as surely as enemy fire, but his oxygen-deprived brain can't recognize the danger. At 30,000 feet, you have approximately 30 to 60 seconds of useful consciousness without supplemental oxygen. This isn't a combat story. This is the story of the engineering that kept WW2 fighter pilots alive in an environment where humans cannot survive. The physics of breathing at altitude, the technology that solved it, and the failures that killed pilots who never saw an enemy. Human physiology evolved for sea level. Atmospheric pressure of 14.7 pounds per square inch. Oxygen concentration of 21%. Your lungs extract oxygen through pressure differential. At 10,000 feet, atmospheric pressure drops to 10.1 psi. You're getting 30% less oxygen with each breath. At 18,000 feet, pressure is 7.3 psi, half the oxygen available. At 25,000 feet, 5.5 psi, your body is starving. And WW2 fighter combat routinely occurred at 25,000 to 35,000 feet, where the air is too thin to sustain consciousness. Here's where physics becomes critical. It's not just about oxygen percentage, it's about partial pressure. The oxygen molecules in the air at 30,000 feet are the same 21% concentration, but there are far fewer molecules per cubic inch. Your lungs can't create the pressure gradient needed to force oxygen into your bloodstream. Aviation medicine calls this pressure-altitude effect. Combat pilots called it the altitude wall. Without supplemental oxygen delivery systems, every mission above 12,000 feet was potentially fatal, and the enemy might never fire a shot. The altitude problem wasn't theoretical. In 1920, U.S. Army pilot John McCready set an altitude record of 34,508 feet. He survived, but reported severe physiological effects: extreme fatigue, impaired judgment, near loss of consciousness. Early aviators attempting high-altitude flight experienced similar symptoms. Pilots would become disoriented, lose consciousness, and crash. Aviation historians recognize these early flights as critical experiments that defined the limits of human endurance. By the mid-1930s, aviation engineers understood the requirement. Fighter aircraft performance was pushing toward 30,000-foot operational ceilings, but pilot survival required supplemental oxygen above 12,000 feet. The Luftwaffe, RAF, and U.S. Army Air Corps all initiated parallel oxygen system development programs. The engineering challenge: deliver pressurized oxygen to a pilot in a violent, maneuvering environment where G-forces, temperature extremes of -60 degrees Fahrenheit, and combat stress already pushed human limits. The solution would require three components: storage, delivery, and interface equipment that wouldn't fail. Oxygen storage in WW2 fighters required engineering that balanced weight, capacity, and safety. Compressed oxygen was stored in high-pressure steel cylinders, typically rated for 400 to 450 psi, though operational pressure was usually 300-350 psi to maintain safety margins. A P-51 MUSTANG carried 2 oxygen bottles, total capacity approximately 38 cubic feet of oxygen at standard atmospheric pressure. That sounds substantial until you calculate consumption rates. At 25,000 feet, a pilot breathes approximately 1.5 cubic feet per minute under normal conditions, higher during combat stress. Theoretical oxygen duration: 25 minutes at high altitude. Combat missions lasted hours. The math didn't work. Here's the engineering innovation. Oxygen delivery systems weren't continuous flow at high altitudes. Engineers developed demand regulators that only supplied oxygen during inhalation, reducing consumption by 60%. Additionally, the oxygen was diluted with cabin air at lower altitudes. At 15,000 feet, you don't need 100% oxygen, just enriched air. Technical manuals confirm that with demand regulation and altitude-based mixing, those 38 cubic feet could sustain a pilot for 4 to 5 hours at combat altitudes. The system worked, but it had zero redundancy. One bottle failure, and you descended immediately or risked hypoxia. The oxygen mask was the critical interface between system and pilot, and its design evolved through brutal trial and error. Early masks were simple rubber face cups with a single delivery tube. They worked at rest. In combat, they failed catastrophically. Under G-forces during aggressive maneuvers, the mask would shift, breaking the seal. Negative G pushover maneuvers could cause the mask to pull away from the face entirely. The U.S. Army Air Forces standardized on the A-14 demand oxygen mask by 1943, a significant improvement featuring a full-face rubber seal, dual check valves for inhalation and exhalation, and a microphone integration for radio communication. The British RAF used the Type E and later Type G masks with similar functionality. Key innovation: the demand system used a spring-loaded diaphragm. When you inhaled, the negative pressure opened the oxygen valve. When you exhaled, positive pressure closed the oxygen valve and opened the exhalation port. This prevented oxygen waste and CO2 buildup. But here's the human factors challenge. Pilots had to achieve an airtight seal against their face for hours. Mask pressure created facial indentation. Pilots who flew long missions would have visible mask marks for hours after landing. The rubber degraded in extreme cold. Ice formation from exhaled moisture could block valves. Regular mask inspection and proper fit were literally life-and-death maintenance items. WW2 oxygen systems used two primary delivery methods, each with distinct advantages and failure modes. Continuous flow systems delivered a constant stream of oxygen regardless of breathing cycle. Simple, reliable, no moving parts to fail, but wasteful. At high altitudes, you'd exhaust your oxygen supply in under 90 minutes. Early war aircraft used continuous flow because the technology was proven. Demand systems, introduced widely from 1942 onward, only supplied oxygen during inhalation. A pressure-sensitive regulator detected when you breathed in and opened the valve. Oxygen conservation increased by 60 to 70%, extending mission endurance from 90 minutes to 4 to 5 hours. But complexity meant failure points. If the demand regulator froze, common at minus 60-degree temperatures, the valve stayed closed. You stopped receiving oxygen. Pilot training emphasized recognition of demand system failure. If you felt symptoms of hypoxia, but your pressure gauge showed adequate supply, switch to emergency continuous flow immediately. The P-47 Thunderbolt had a manual emergency bypass lever. Pull it, and you got continuous high-flow oxygen regardless of regulator status. This override consumed your entire supply in 20-30 minutes, but it kept you conscious long enough to descend to breathable altitude. Technical manuals confirm that oxygen system failures accounted for more non-combat losses than acknowledged in official records. Here's where engineering philosophy diverged across nations. The US and Britain prioritized pilot endurance with high-capacity demand systems. American P-51s and P-47s could operate at altitude for 4 to 5 hours. German Luftwaffe oxygen systems, particularly on the Bf-109 and FW-190, used smaller capacity bottles with continuous flow systems. Endurance at combat altitude was approximately 60 to 90 minutes. This wasn't inferior engineering. It reflected tactical doctrine. German fighters operated primarily over occupied Europe with nearby bases. Short-duration interception missions didn't require extended oxygen supplies. American bombers penetrated deep into Germany, and their fighter escorts needed endurance to match. Japanese oxygen systems demonstrated the most significant limitations. Early War Zero fighters had minimal oxygen equipment, relying on pilot tolerance to altitude effects. Later variants incorporated basic oxygen systems, but capacity remained limited. The result? Japanese pilots at altitude often operated at physiological limits. Combat reports verify that Japanese fighter effectiveness decreased markedly above 25,000 feet, not due to aircraft performance but pilot oxygen deprivation affecting reaction time and decision-making. The RAF developed the most sophisticated pressure breathing system by 1944, allowing pilots to operate effectively at 40,000 plus feet. We'll examine that technology shortly. Combat reports document oxygen system failures with disturbing frequency. What would you have done in the pilot's position? Continue the mission or abort? Comment your tactical decision below. December 1944, 8th Air Force mission over Germany. A P-51 pilot's oxygen system fails at 28,000 feet during escort duty. Standard procedure, immediate descent to 12,000 feet or below. But the bomber formation he's protecting is under attack. He stays at altitude, accepting progressive hypoxia, maintains formation position for 15 minutes until relief fighters arrive, then descends. Post-flight medical examination confirmed cognitive impairment and delayed reaction times. He'd been operating with significantly reduced oxygen for a quarter hour. Another scenario. P-47 pilot experiences frozen oxygen regulator at 32,000 feet. He recognizes the symptoms, the training works, and immediately switches to emergency continuous flow while descending. His oxygen supply exhausts at 18,000 feet, but he's already below the critical altitude threshold. He makes it home. The pilots who didn't recognize the symptoms didn't survive to file reports. Aviation historians note that hypoxia is insidious because your brain, the organ detecting the problem, is the organ being deprived of oxygen. Your judgment fails before you recognize you need to act. This made oxygen system reliability as critical as engine reliability. By 1944, aviation engineers faced a new challenge. Aircraft like the P-51H and late war jets were reaching 40,000 plus feet. At that altitude, even 100% oxygen through a demand mask isn't sufficient. The partial pressure of oxygen is too low. Your lungs physically cannot extract enough oxygen even breathing pure O2. The solution: pressure breathing. Instead of waiting for you to inhale and create negative pressure, the system actively forces oxygen into your lungs under positive pressure. The RAF developed the pressure waistcoat system. Pilots wore an inflatable vest connected to the oxygen regulator. As altitude increased above 38,000 feet, the vest inflated, applying pressure to the chest and abdomen. This countered the positive pressure in the lungs, allowing the pilot to exhale against the incoming oxygen flow. Without the counterpressure garment, pilots couldn't exhale. the positive oxygen pressure would overinflate their lungs. American test pilots evaluated pressure, breathing systems in the P-80 jet prototype. They reported that breathing required conscious effort. It felt unnatural, almost like breathing underwater. Physical exertion during combat, while pressure breathing caused rapid fatigue. But it worked. Pressure breathing extended human operational altitude to 45,000 feet. By 1945, it became standard equipment for extreme high-altitude interceptors. Oxygen system technology only worked if pilots recognized when it failed. Aviation medicine developed hypoxia recognition training, still used today, that placed pilots in altitude chambers. Trainees would ascend to 25,000 feet in a depressurized chamber, then remove their oxygen masks. Instructors observed as hypoxia symptoms manifested: loss of peripheral vision, euphoria, impaired judgment, slowed reactions. The critical lesson: you don't feel like you're dying. You feel great, giddy, happy, unconcerned. Then you lose consciousness. Training emphasized 3 hypoxia indicators: fingernail cyanosis, your nails turn blue-gray from oxygen-deprived blood; cognitive impairment, simple math problems become impossible; emotional changes, inappropriate laughter or apathy. Every WW2 combat pilot experienced altitude chamber training. They learned their personal hypoxia symptoms. Everyone's slightly different, and the point of no return. Official specifications show that at 30,000 feet, time of useful consciousness averages 30 to 45 seconds after oxygen loss. That's how long you have to recognize the problem, diagnose the cause, and execute emergency procedures before you're incapacitated. Pilots who survived oxygen failures universally credited their training. The ones who didn't recognize symptoms in time never got to explain what went wrong. Temperature at 30,000 feet averages minus 60 degrees Fahrenheit, cold enough to freeze moisture instantly, and oxygen systems contained moisture. Every breath you exhale contains water vapor. In the oxygen lines and regulator components, this moisture would freeze, forming ice crystals that could block valves, freeze diaphragms, and shut down the entire system. Aviation engineers addressed this through multiple approaches. First, moisture traps. The oxygen delivery line included a water separator that collected condensation before it reached the regulator. This reduced but didn't eliminate moisture. Second, heated oxygen lines. Later war, American fighters routed electrical heating wires along oxygen lines to prevent freeze-up. The P-51D's oxygen system included thermostatically controlled line heating activated above 20,000 feet. Third, cold weather oxygen. Ground crews at bases in England, Italy, and the Pacific learned to pre-dry oxygen bottles by running them through desiccation chambers. This reduced the moisture content in the compressed oxygen itself. But combat reports verify that despite these measures, frozen regulators remained a persistent problem. Pilots operating in European winter conditions at high altitude would feel their masks stiffen as exhaled moisture froze on the rubber. The ice would accumulate around the exhalation valve, potentially blocking it and causing CO2 buildup. Standard procedure: periodically flex the mask to crack accumulated ice and clear the valves. Oxygen system maintenance was as critical as engine maintenance and more frequently neglected. Technical manuals specified inspection intervals. Oxygen bottles tested for pressure integrity every 30 days. Regulators disassembled and cleaned every 50 flight hours. Masks inspected for cracks and seal integrity before every flight. Ground crews at forward bases under combat conditions often couldn't meet these intervals. Museum archives document that oxygen system failures increased significantly when maintenance schedules slipped. The pressure test was critical. Bottles were filled to operational pressure, then monitored for 24 hours. Any pressure drop indicated a slow leak, unacceptable for combat operations. The regulator cleaning procedure required specialized training. Dust, oil contamination, or debris in the diaphragm chamber would cause malfunction. But here's the maintenance challenge. Oxygen systems were low-visibility components. Unlike engines or flight controls that announce their failures dramatically, oxygen systems failed silently. A pilot wouldn't know his regulator was malfunctioning until he reached altitude and began experiencing hypoxia symptoms. Pre-flight oxygen checks became mandatory. At engine start, every pilot performed a breathing test. Inhale deeply, verify resistance from demand valve. Exhale, verify exhalation valve operation. Check pressure gauge for adequate supply. This 30-second check saved countless lives by catching system failures on the ground. Fighter pilot oxygen systems were individualized. Bomber oxygen systems had to support 10 crew members simultaneously for 8 to 10-hour missions. The B-17 Flying Fortress carried 4 large oxygen bottles, total capacity approximately 250 cubic feet. Distribution lines ran throughout the aircraft: cockpit, navigator station, bombardier position, radio room, waist guns, tail gun position. Each position had a regulator and mask. The engineering challenge: maintaining pressure throughout a 70-foot aircraft with multiple simultaneous users. The solution employed pressure-compensating distribution manifolds that ensured equal pressure at all stations, regardless of how many crew members were drawing oxygen simultaneously. But this created a critical vulnerability. Combat damage to the distribution lines could depressurize the entire system. B-17 and B-24 crews experienced oxygen lines severing from flak and fighter attacks. Standard procedure: portable walk-around bottles. Crew members needing to move through the aircraft carried small emergency oxygen bottles, providing 10 to 15 minutes of supply. This allowed the wounded to be moved, fire suppression in unpressurized areas, and emergency repairs. The waist gunners and tail gunner operated in unheated sections at -60 degrees, while breathing pure oxygen through masks for hours. Aviation medicine documented that bomber crews experienced higher rates of frostbite and cold weather injuries than fighter pilots due to extended exposure in oxygen-dependent environments. When a pilot bailed out at high altitude, oxygen deprivation remained the threat. Standard parachute descent rate: approximately 1,000 feet per minute. From 30,000 feet to safe breathing altitude at 12,000 feet required 18 minutes of descent. But you only had 30-45 seconds of consciousness without oxygen. The solution: bailout oxygen bottles. American pilots wore a small emergency oxygen bottle clipped to their parachute harness, capacity sufficient for 10 minutes. British pilots used a similar system. Bailout procedure: pull emergency oxygen bottle activation handle, verify flow through mask, then exit aircraft. The emergency bottle would sustain you during the initial descent through lethal altitude. But combat reports verify that in the chaos of emergency bailout, aircraft on fire, structural failure, combat damage, pilots sometimes forgot to activate the bailout bottle. They would exit the aircraft, descend through 25,000 feet, lose consciousness, and regain awareness at 10,000, 12,000 feet as they entered breathable atmosphere. If the parachute had already automatically deployed, they survived. If not, they didn't. Training emphasized the emergency oxygen activation as part of the bailout sequence. Canopy jettison, oxygen bottle activation, harness release, exit aircraft. The sequence was drilled until it became automatic. Because at 30,000 feet, with seconds of useful consciousness remaining, you don't have time to think. Only react. The WW2 oxygen system engineering established principles still used in aviation today. Modern fighter pilots at 50,000 feet use descendant technology, pressure breathing with anti-G suits, demand regulators with digital flow control, redundant oxygen generation systems. Commercial airline passengers don't realize they're experiencing WW2-era technology every flight. Aircraft cabin pressurization became standard because oxygen systems couldn't practically support hundreds of passengers. The B-29 Superfortress pioneered pressurized crew compartments, eliminating the oxygen mask requirement for most crew positions. This innovation carried directly into post-war commercial aviation. Combat reports verify that WW2 oxygen system development saved thousands of pilots who would have been lost to altitude effects. The engineering solved a fundamental human limitation: our inability to survive in the environment where modern warfare occurred. Aviation historians recognize WW2 oxygen systems as critical life support technology that enabled strategic bombing campaigns, long-range fighter escorts, and high-altitude air superiority. The simple demand valve regulator, the pressure breathing system, the emergency procedures, all born from desperate necessity in 1940s aerial combat, remain fundamental to aviation safety today. So how did they breathe at 30,000 feet? Through engineering that balanced physics, physiology, and reliability under the most demanding conditions humans have created. Compressed oxygen storage at 400 psi. Demand regulators that conserved supply while delivering precisely when needed. Masks that sealed against G-forces and extreme cold. Emergency systems that provided backup when primary systems failed. And trainings that taught pilots to recognize when their brain was being starved of oxygen before cognitive function collapsed completely. Official specifications show that oxygen systems had failure rates higher than any other aircraft system, yet they worked well enough to enable the strategic air war. Combat reports verify that thousands of pilots survived missions that would have been fatal without supplemental oxygen technology. This is the pilot historian. If you learned something about the technology that kept WW2 pilots alive at altitude, subscribe for more aviation engineering analysis every Tuesday and Saturday. The next time you're on a commercial flight and the safety briefing mentions oxygen masks, remember, that system exists because WW2 engineers solve the problem of breathing where humans cannot survive.